Imagine challenging decades-old beliefs about how solids behave when pushed beyond their limits. This is exactly what a team led by Bob Nagler and Thomas White achieved by developing a groundbreaking way to measure atomic temperatures in warm, dense matter. This new approach measures the speed of atoms in materials heated to extreme temperatures, providing fresh insight into the mysterious realm of superheating and the boundaries of solid matter. Every material has its own melting and boiling points, but under certain conditions, it can be heated beyond these points without instantly melting or boiling. This state, known as superheating, typically ends abruptly in what's called an entropy catastrophe, a sudden and uncontrollable phase change. But here's where it gets controversial. When the research team superheated solid gold to a staggering 19,000 kelvins, far beyond the predicted limits, it surprisingly did not succumb to this catastrophe. This suggests that if heated quickly enough, materials might not have a fixed maximum temperature for superheating after all. Laser Focus World asked Bob Nagler and Thomas White about the inspiration behind superheating gold using the Linac Coherent Light Source, LCLS, at SLAC National Accelerator. Bob explains that their main goal was to develop a novel way to directly measure the temperature in warm, dense matter, a type of matter as tightly packed as solids, but heated to tens or even hundreds of thousands of kelvins. This state of matter appears naturally in places like the cores of giant planets and stars, but actually measuring its temperature in the lab has been notoriously difficult. They aimed to tackle this challenge using the unparalleled brightness of the LCLS X-ray source. Thomas adds that the idea didn't spring from a sudden stroke of genius, but rather from ongoing frustrations within the scientific community about temperature measurements in extreme states. Gold was chosen because it scatters X-rays effectively and can be formed into very thin foils, making it ideal for their technique. Their initial expectation was that irradiating the gold would heat it, but the shock came when the solid retained its orderly, crystalline structure even at these blistering temperatures. The gold's lattice remained intact beyond what thermodynamics would normally allow, and this surprising discovery shifted their project's focus. What started as an attempt to create a better temperature measuring tool evolved into a deeper investigation into superheating and the fundamental limits of solids under intense conditions. So why was LCLS indispensable? Thomas explained that their method hinges on observing slight shifts in the energy of X-rays scattered off atoms, which directly reveals the ion's temperature. This requires not just intense brightness, but also extremely narrow energy bandwidth. Free electron lasers like LCLS and similarly the European XFEL are uniquely equipped for this. Their intensity is about 1 billion times greater than traditional synchrotrons, which is crucial because the signals they measure, called inelastic scattering, are incredibly faint, just a handful of photons per laser pulse. In Bob's words, LCLS essentially functions as a kilometer-long laser thermometer with unmatched brightness, coherence, and spectral precision. Without these qualities, this kind of measurement simply wouldn't be achievable. The experiment itself involved heating a super-thin gold foil, only 50 nanometers thick, using a frequency-doubled titanium sapphire laser, producing light at 400 nanometers with ultra-short 45 femtosecond pulses. Interestingly, the laser power was modest, about 0.3 millijoules per pulse, meaning this superheating technique could be replicated in many laser labs worldwide. But here's the catch. While creating superheated gold can be done in many places, measuring its temperature with such precision requires the unique capabilities of an XFEL like LCLS. What did they learn? One of the biggest breakthroughs was achieving a direct, model-independent measurement of ion temperatures in these extreme states, a long-standing challenge in high-energy density physics. This new technique paves the way for validating equations that describe matter under extreme conditions, improving simulations, and exploring previously unreachable experimental realms. The real surprise, Thomas recalls, was discovering how resilient the crystal lattice of gold was. it remained ordered at temperatures more than 14 times its normal melting temperature, a finding that defied traditional thermodynamic predictions. This revelation was a turning point, showing that their work wasn't just solving a technical problem, but unveiling new physics about how solids behave under ultra-fast extreme heating. When asked about disproving long-held theories, Thomas emphasized that it wasn't a simple matter of overturning old ideas. Instead, the existing theories don't necessarily apply to these rapid, far from equilibrium situations where matter is blasted by femtosecond laser pulses. These theories assume systems slowly reaching equilibrium near melting points. So the experiment, in a way, explored entirely new territory beyond their scope. This raises a provocative question. Could there be no true upper temperature limit for superheated materials if heated under such intense, rapid conditions? Bob sees it as an invitation to explore how far superheated matter can deviate from expected behavior when it's driven far from equilibrium. In the broader context of high-energy density physics, Bob highlights that measuring temperatures accurately has been a missing experimental tool for years. Their method fills this gap and has important consequences for fields like geophysics, planetary science, astrophysics, and even the pursuit of fusion energy. Speaking of fusion, while the technique isn't designed to measure the temperatures inside fusion fuel, which can be much hotter, it holds significant implications for the materials surrounding that fuel. Understanding how solids endure the extreme radiation and particle environments in fusion reactors is crucial for developing durable reactor components. Looking ahead, the team has already conducted experiments measuring the temperature of iron as it undergoes shock melting, using high-energy, long-pulse lasers. These studies are vital for understanding Earth's core, which is primarily iron, pushing laboratory research closer to simulating planetary interiors. The promising initial data hints at a wealth of new knowledge awaiting discovery. Moreover, they plan experiments targeting materials and scenarios relevant to inertial confinement fusion, particularly examining matter's behavior under intense radiative and particle bombardment. This research challenges us to rethink the fundamental physics of superheating and melting under ultra-fast, non-equilibrium conditions. But here's the part most people miss. Could redefining these limits change how we design materials, simulate planetary conditions, or develop fusion energy? Are traditional thermodynamic concepts still sufficient, or do we need new theories for these extreme states? What do you think? Does this open a new frontier in material science, or does it simply reveal the flexibility of existing models? Share your thoughts and let the debate begin.